I'm going to go over free response question number 2 from the 2021 AP Calculus BC exam. We're told that for time t greater than or equal to 0, a particle is moving in the xy plane with the position given by x of t, y of t, and we're given a velocity vector. Now we know that velocity is the first derivative of position, so we know that this right here is x prime of t and y prime of t. And since I have a feeling we're going to be using these a lot, let's go ahead and stick them in the calculator right away. Now I put my calculator into parametric mode for this question. You don't have to do that, but I did. So x1 of t, I'm going to put in here our x prime of t, because that's what we're given. And that was, oh, why did it give me 3 of those? We just want t minus 1 times e to the t squared. So this was our x prime of t. And our y prime of t, which I'll put into here, is going to be the sine of t to the 1.25. And now let's go, ooh, why did it jump down? I don't know why I did that. Let's go back up and put in a closed parenthesis at the end. And now let's go and read part A. We have to find the speed of this particle at t equals 1.2. Well, we know that the speed is just going to be the square root of x prime of t, and we're using t equals 1.2 squared, plus y prime of 1.2, squared. And we're going to do this in the calculator, so I'm going to put this in when t equals 1.2. We're going to have, so let's go back here. We're going to do a square root, and we're plugging this in here, so let's open a parentheses. We have 1.2 minus 1 is 0.2 times e to the 1.2 squared. And this is our x prime of 1.2, so we have to square that. And then we have to add it with y prime of 1.2. So we know that y prime of t was just sine of t to the 1.25, so we'll put in here not 0, but sine of 1.2 to the 1.25. And then we'll close this, and square, and we'll get a value. So we have, this is equal to 1.271. Now we have to find the acceleration vector of the particle at time t equals 1.2. Well, we know that acceleration is the first derivative of velocity. So for the acceleration, we know that that's going to be this, well, it's going to be a vector, so let's just open a vector like this. And we know it's going to be x double prime of 1.2 and y double prime of 1.2. And again, we're going to do this in the calculator. So to get the x double prime, I'm going to do a derivative. So we'll go to math number 8, d dt, and we want to differentiate our x prime, which I stuck into that x sub 1 of t. So we'll put that in right here. And we were doing this at t equals 1.2. So let me bring this in here so you can see it. 6.247. So 6.247. And we'll do y double prime of 1.2. So I'm going to go again into my derivative and go over to here and put in my y sub 1 of t, which was my y prime of t, at t equals 1.2. And this is going to be 0.405. And we're done with part A, and we'll move on to part B. Okay, so for part B, we have to find the total distance traveled by the particle over the time interval from 0 to 1.2. Well, we know to do that, we have to integrate, and we're going to be doing this from 0 to 1.2, and we have to do the square root of x prime of 1.2 squared plus y prime of 1.2 squared. This is basically the parametric arc length, which will give us the distance traveled by the particle. And now we'll go ahead and put this in the calculator. So we'll say integral from 0 to 1.2 of the square root, and we have x prime of 1.2, so when we plug in 1.2 for the x prime right here, we're going to have 0.2 times e to the 1.2 squared. Oh, actually, I don't want to have a closed parentheses here. I want to have a closed parentheses right here, because now I have to square this. Then plus, this was my x prime of t squared, now I have to do y prime of t squared, so that's just going to be the sine of 1.2 to the 1.25, 1.25, close that, square that, and this was going to be dt, and we get our value right here. So we'll say that this equals 1.526. And now let's move on to part C. Okay, so for part C, we have to find the coordinates of the point at which the particle is farthest to the left for t being greater than or equal to 0. Well, let's think about any parametric curve right here. Where is the particle farthest to the left? Well, it's the minimum value of x. So how can we find the minimum value of x? Well, we can set x prime of t equal to 0 to find the critical values. So we want to set x prime of t, which is t minus 1 times e to the t squared, equal to 0. And yes, you can use the calculator for this, but I'm not going to bother because e to the t squared is never 0. So we only need to set this part equal to 0, so I think it's pretty easy to see that the only critical value here is t equals 1. And the point that we care about is therefore going to be x of 1, comma, y of 1. So now we just have to find x of 1 and y of 1. Well, x of 1, how can we do that? We have an initial condition right here. For t equals 0, x is negative 2. So I want to have an x of 0 right here, plus, this is going to be the integral from 0 to 1 of x prime of t dt. If you think about the fundamental theorem of calculus here, the integral from 0 to 1 of x prime of t dt is going to be x of 1 minus x of 0. And the x of 0s will cancel out, and you'll just be left with a true equation. Similarly, for y of 1, this will be equal to y of 0 plus the integral from 0 to 1 of y prime of t dt. So to get x of 1, we're going to take x of 0, which was negative 2, and we're going to add the integral from 0 to 1 of x prime of t, which I've already stored in my x sub 1 of t. Oh, that's not where I wanted to go. Let's try that again. I want to go into parametric, put in my x1 of t, et. So this is my y-coordinate right here. So this is going to be negative 2.603. Sorry, that's my x-coordinate. Then my y-coordinate right here is going to be y of 0, which is 5, plus the integral from 0 to 1 of y prime of t, which again is stored in my y sub 1 of t dt. And there's my y-coordinate, 5.41. I don't think you have to put down 5.410. I think you can just leave it like that. All right, now let me get a clean screen so we can think about the final part of this question. Let me label this again. This is x prime of t and y prime of t So we have to explain why there is no point for which the particle is farthest to the right at t equals 0. Well, if there were a point at which the particle were farthest to the right, that means x would have to have a maximum. So basically what we have to show is that x doesn't have a maximum. And in a sense, we've already done that because we've shown that the only critical value is at t equals -1. So we basically have to show that that is a minimum. Well, how can we do that? If it's a minimum, that means that the slope will change from negative to positive. So let's take a look at some values here. Let's take a look at x prime of 0, x prime of 1, and x prime of 2. Well, x prime of 0, you plug that in right here, you're going to have 0 minus 1, which is -1, times e to the 0 is still a -1. Put in 1 right here, you get 0. Put in 2 right here, you're going to have 2 minus 1, which is 1, times e to the 2 squared. So you're going to have e to the 4th. So the slope does change from negative to positive at t equals 1. So I'm going to pull up my notepad. Again, on the exam, you have to handwrite all this, but since it's kind of hard to write on the computer screen, I'm going to do a little typing. So there is no point at which the particle is farthest to the right because x of t has no maximum value. And I think that would be an okay explanation for this. Perhaps you should put something on here about how at the only critical value t equals 1, you could say that the slope changes from negative to positive, therefore x of 1 is a minimum.